Now that we know how to graph sine and cosine, tangent and cotangent, secant and cosecant, it's time to start talking about the inverses of these functions. Now, we could have talked about the inverses of these functions back in chapter 6 when we were doing chapter 6 before we did chapter 5. But I held off because I think it makes much more sense to talk about the inverse of a function if you can talk about it from the graphical perspective. For example, if I take y equals x squared and draw its graph, I can talk about the fact that x squared, y equals x squared, is a function because it passes what we call the vertical line test. The vertical line test tells us that for any given value of x, there is exactly one value of y associated with that value of x. Now, if I take a look at y equals plus or minus the square root of x, I get this graph. Approximately. And for any given value of x, there can be more than one value of y associated with that value of x. That is why y equals plus or minus the square root of x is not considered a function. It fails the vertical line test. A vertical line passes through the function more than one time. Even if there are places where it only passes through the function once, such as here at the origin, the fact that it passes through the function more than once anywhere makes it not a function. That's the graphical explanation. The logical explanation is that given a value of x, if I can only find one value of y associated with that value of x for any value of x, then it's a function. If there's anywhere at all in the graph, that second value of y might be assigned to that value of x, then it's not a function. Now, if I'm graphing and playing around with y equals x squared, and I don't care about whether it's inverse as a function or not, then that's fine. I can just leave it as it is. But if I want to switch back and forth between the function and its inverse, then I have to say that x has to be greater than or equal to 0 for this function in order for me to be able to talk about its inverse. When I do that, I end up getting y equals the positive square root of x only. And so that means the graph down here, this part of the graph, doesn't exist. And now it passes the vertical line test. So in order to make this inverse function a function at all, it has to have, the original function has to have its domain restricted. And that's exactly what we're going to be doing with sine and cosine, tangent and cotangent, secant and cosecant. We'll start with sine. We're back to, at the moment at least, dealing with my hand-drawn graphs, which isn't always ideal. But I think it's important to talk through the theory, to talk through where these ideas come from, and to really look at them in detail before we start just blithely graphing them on a calculator or on Desmos. So I'm going to start by graphing the function sine. Let's see, if that's a 1, and I'm going to call, well, I'll just do this. I'll call this 2 pi, which makes this pi, and this pi over 2. This is 3 pi over 2. Now, I do have pi over 4 and 3 pi over 4, and I have all these other values in here as well, but I don't necessarily need to graph every single one of these points now that I know what the function looks like. For sine, I know it starts at the origin, and it ends at the origin, and it goes through the origin again at pi. Halfway between, and this is a standard sine function, it's not flipped, stretched, compressed, or shifted in any way, it's just y equals the sine of x. Halfway between 0 and pi, it reaches its maximum value of 1, and halfway between pi and 3 pi over 2, it reaches its minimum value of -1. And when I connect the dots, I get something that looks like this. There's my sine graph. Now, the sine of x passes the vertical line test. No matter where I draw a vertical line through the sine function, it only crosses through the function once. So therefore, the sine of x is a function. For every value of x, there is only one associated value of y. And that's true not only between 0 and 2 pi, but everywhere, because this pattern keeps going on forever in both directions. So we don't have to restrict the domain of sine at all, as long as we're interested only in the sine. But if we want to find the inverse of sine, we have something else we need to consider. Let's go back up to x squared. A minute ago, we confirmed that y equals x squared was a function by checking that for each x, we didn't check all of them, but you can see that any vertical line drawn to the graph of the function y equals x squared is only going to pass through that function's curve once. And that's fine for telling whether it's a function or not, but how could I tell on this graph whether or not it had an inverse? Well, basically, the function y equals x squared has an inverse, the graph of which is just this function, the original function, flipped over the line that is y equals x. Now, it turns out that that means that in this case, it looks like it's on its side. This looked like a quadratic, like a parabola before I erased half of it, but it was on its side. And so in order to pass the vertical line, in order for the inverse to pass the vertical line test, the original graph has to pass the horizontal line test. So let's use a horizontal line now. And we can see that for any value of y, this is one way to think of it, for any value of y, does this graph, can you trace it back to only one value of x? And the answer is no. I can trace it to this value of x, and I can trace it back to this value of x. I'll call those x0 and x1, two different x values. So the fact that this goes to two different x values, or two different x values give you the same y value, means that in the inverse, the x value is going to potentially have two y values associated with it. So the vertical line test just tests whether the thing is a function. The horizontal line test tests whether it's what we call a one-to-one function, and that is that it will, if it does pass the horizontal line test, then it has an inverse just in its current form. If it doesn't pass the horizontal line test, let me get my pen here. If it doesn't pass the horizontal line test, then you can restrict the domain so that what's left of it will pass the horizontal line test, and therefore the inverse will exist and will pass the vertical line test. And so that's what we need to do here. Notice that the sine fails the horizontal line test. That for a given y value, that looks like about a half, there are going to be more than one, and in fact there's an infinite number, because there's a couple more there, and if we keep going, a couple more here, there's more than one x value that will give us this y value. So if we want to be able to talk about the inverse of sine, we need to restrict its domain. Okay, I've erased the extra cycles of sine that I had graphed, and I was going to try to make do with this graph here, but I think I'm going to redraw it. Okay, that's better. A clean copy. All right, now back up here with x squared, we said that if the function failed the horizontal line test, we needed to restrict the domain so that, like if I erase this part here, then when I flip this over the line y equals x, I'd end up with the y equals the positive square root of x graph. So I have to figure out what part I want, or what part I'm allowed to keep, so that the inverse graph makes sense as a function. So in this case, it looks like at first glance, it looks like maybe I should keep this piece, the piece from 0 to pi, but that will fail the horizontal line test. So will the piece between pi and 2 pi. The piece that doesn't fail the horizontal line test, and the biggest piece we can get from that, is the piece from pi over 2 to 3 pi over 2. Let's highlight that. So that piece of the function right there is the domain that we're looking at here, pi over 2 to 3 pi over 2. we could argue that's the domain that we could restrict sine to that domain and be able to talk then about the inverse function of sine, or the inverse sine. Let's take a look at what that would look like when I flipped it over. Remember that what an inverse does is takes the values you have for x and y and switches them. So up here, I might have the point, well, that's not a good example. Let's go with 2, 4. This point right here is 2, 4. The corresponding point on the inverse function is 4, 2. This is 4. The height is 2. Whereas here I have 2, and the height is 4. So for each point that I have on sine, I'm going to graph the inverse point, if you will, over here on my inverse function. So where I have 0, 0, I will have 0, 0. Where I have on sine pi over 2, 1, I'm going to have 1, pi over 2. So far, it doesn't look any different, right? So I've grabbed this point here, 0, 0, and then I've grabbed this point here, pi over 2, 1, but I've reversed the x and y coordinates. So 0, 0 became 0, 0, no change. Pi over 2, 1 became 1 pi over 2. The next point of interest is pi, 0. So I'm going to change that to 0, pi. And that's there. So far what it looks like we have is something like that. That's not the greatest job I've ever done either. What's the next one? The next point is 3 pi over 2, negative 1. 3 pi over 2, negative 1. So on my inverse function graph, I'm going to have negative 1, 3 pi over 2. Continuing the curve I had before, I get something that looks like that. Now I've run out of room, so I'm going to erase this dividing line that I put in here earlier. Let's get rid of that for now. I need to make my y-axis longer. There we go. And my last point, or at least the last point on this one cycle of sine, is 2 pi, 0. So I'm going to plot that as 0, 2 pi. And that's there. And I'll finish my curve. Now that's not the nicest sine curve or inverse sine curve that I've ever drawn, but it'll do. It makes the point. And the point is that it's going to fail the vertical line test. So as it is, this is not a function. Let's go back to our sine curve, and we said that the longest stretch of the sine curve, one cycle of the sine curve that we could grab that would pass the horizontal line test was this bit between pi over 2 and 3 pi over 2. The corresponding piece on the inverse function is this piece right here. So if we can go in terms of sine between between pi over 2 and negative 3 pi over 2 for x, we're going to go between pi over 2 and 3 pi over 2 for y for our inverse sine curve. So when I talk about the inverse of the sine function, I have to do it so that the x value for sine, notice how up here, back up in x squared, I restricted the domain for the real function, for the original function. I'm going to do the same thing here. For the original function, sine x has to be between pi over 2 and 3 pi over 2. Now, don't get too stuck on that just yet, because there's something else we need to talk about. It's conventional to talk not about this first full positive cycle of sine as having restricting the domain to pi over 2 to 3 pi over 2, but instead to restricting the domain, let me grab a different color of highlighter, from negative pi over 2 to positive pi over 2, and that would do this in the, sorry, grab my highlighter here. This would mean that we were looking at, not that whole thing, this piece of the inverse sine function. So let me fill that out here. If I were graphing the inverse sine by graphing inverted points, xy becomes yx, then this is what I would have for the inverse sine function, right? But it's not a function if it doesn't pass the vertical line test, so we restrict the domain. Now we can either restrict the domain to this piece here, or to this piece here, or to some other piece, in fact. But it's conventional to restrict it to this piece here. And on the original graph, that's negative pi over 2 to positive pi over 2. And I think probably the main reason for that, let me put my negative pi over 2, put my labels in here. I suspect the main reason for that is symmetry. We have, with this segment of the sine curve, we have a symmetry around the origin, the point 0, 0. We can see very clearly from this that this is an odd function because it's symmetrical around the line y equals x. So instead of restricting our domain from pi over 2 to 3 pi over 2, we're going to restrict it to the window, the range of values negative pi over 2 to positive pi over 2. And this is what we call the domain restrictions on sine, so that we can talk about the inverse of sine. Now, notationally, we have a couple of things we can do here. We will say sine inverse of x is a function. I'll just call it y for now. And this is the graph of y equals the sine inverse of x. And also oftentimes you'll see y equals arcsine of x. These two things mean the same thing. They're equivalent. You can use either of these two notations. If you see either of these two notations in a textbook or in an exam, if you see one, you can interpret it as the other. Now, what it means to be the inverse sine of something, since let's use a numerical example here. Let's say that the sine of pi over 4, we know this to be the square root of 2 over 2. And this is my x value, my input value, my independent variable. This is my y value, my output variable, my dependent variable, my output value, sorry. So the sine inverse, then, remember that inverses switch the roles that x and y play in an equation. So if the sine of pi over 4 is root 2 over 2, the sine inverse of root 2 over 2 is pi over 4. If I'm looking for the sine of something, the something is an angle. The output, the answer, is a number. The sine inverse has an answer that is an angle. The input is a number. Another way to think of this is to say the arcsine, or the sine inverse of root 2 over 2, is the angle whose sine is root 2 over 2. Because the sine of this angle is root 2 over 2. The sine of this angle is root 2 over 2. Those two things mean the same thing, right? Notice that the input for sine is the output for sine inverse, and vice versa. Okay, there are a couple more concepts we need to deal with in this topic, so I'm going to move to a new slide and we'll talk about those over there. The first of these is the idea that the inverse is an operation. I'm going to use y equals x squared again as my example. Since the inverse, that's y inverse, is the square root of x, we can think about composing these functions as y of y inverse of x, or y inverse of y of x. And remember that inverses essentially cancel out whatever the original function did to x. So in this case, I'm going to have y inverse of x on the inside, and I'm going to do to that whatever y told me to do, which was to square it. And the answer is x. In this case, I'm going to have y of x, which is x squared. And then I'm going to do to this what I'm told y inverse does to functions, and that is to take the square root. And the result, again, is just x. And this is what inverses do. The composition of y with y inverse, or y inverse with y, is just x. If I call this f of x instead, and I call this one f inverse of x, then I can use the notation that I'm more familiar with. I'll do it down here. F of f inverse of x, or f inverse of f of x. And sometimes you see, I'll do this one here. This is equivalent to f composed with f inverse, and this one's equivalent to f inverse composed with f. So let's see how this plays out with sine. If my function f of x is sine of x, then my function f inverse of x is sine inverse of x, or you might say arcsine of x. So what is f composed with f inverse? Remember that this notation means the function f operating on the function f inverse. So I'm going to have my inside function here, which is f inverse, that is arcsine or sine inverse. And on that function, I'm going to perform this operation, which is do f to this thing, and f is the sine of x. So I'll have the sine of the sine inverse of x. And because sine inverse does one thing to it, and sine undoes that, that's what inverses do, the result is just going to be x. And it turns out that, as is the case with inverses, f inverse composed with f means take f of x this time. Sorry, I'm having trouble with my pen here. Take f, whatever that was, and it turns out that's just the sine of x. Take that, that's the inside function, that's the thing you're going to operate on, and do this to it. Take the inverse of it. So the sine inverse of the sine of x is also just x. Now we have to be careful here, because remember that in order to talk about sine inverse at all, we had to restrict the domain on sine. So if I take the sine of a number, I'm looking at this example here, if I take the sine of a number, let's go to the inside first. The sine inverse of x, the sine inverse of x, let's call that y equals for the moment. And remember that if you put a number in here, the number that you're putting in here is an angle. So the answer to the question, what is the sine inverse of x? The answer to the question is, it's the angle whose sine is whatever number is in here. So my previous example was, let me move this around a little bit. If I have y equals the sine of x, and I said that the sine of pi over 4 was root 2 over 2. This is my x value in this case, and this is my y value. This is my input, this is my output. But the sine inverse says, what is the angle whose sine is root 2 over 2? And the answer is pi over 4. In this case, this is my input, and the output is an angle. So the output here, the answer to sine inverse, is going to be some angle. And angles can go on, we can have any number of angles, right? We can have angles between 0 and 360, or 0 and 2 pi, or we can have an angle that's 4 pi, or 12 pi, or negative 720 degrees, right? The angle can be any value. There's no restriction on how big the angle can be. This can be as big as we want, or as small as we want. But when I take the sine of that number, sure, I'm going to get x. But because I know how sine behaves, I know that x is going to be between negative 1 and 1. The answer to this question is some angle. Might be small, might be huge, might be positive, might be negative. Whatever that angle is, take the sine of that angle, and the answer has to fall between negative 1 and 1, because sine only goes between negative 1 and 1. On the other hand, if I take the sine of a number, then that's got to be between -1 and 1. And if I then take the inverse of that, I must have restricted the domain on sine in order to be able to take this inverse. I had to restrict the domain on sine. And so my answer is still going to be x, but it's going to be some number between -π/2 and π/2. This is in a box on page 440 in your textbook, at least in the current edition. You don't necessarily have to memorize this, but you do have to be thinking very carefully about it as you work through the problems in this section, and in anytime you see this idea in the future. We're going to be doing some simpler problems where we just evaluate sine inverses like this. I'll give you a question like this, and I'll ask you, okay, what is your y value? Well, the y value is the angle whose sine is √2/2, so it's π/4. But it's only π/4 because π/4 is between -π/2 and +π/2. Okay, so keep this in mind as we go forward. And let's do another screen now, another slide, to talk about some examples. We'll start with some simple ones like this, and then we'll work on taking the sine of the sine inverse and the sine inverse of the sine. Okay, here are three functions that need to be evaluated. The sine inverse of 1/2, the sine inverse of -√3/3, that should be √3/2. I always do that. And the arcsine of √2/2. Now remember, arcsine just means sine inverse. I've just thrown it in here to help us see that. I want you to get used to seeing them both and being able to think of them as equivalent. So the question we're asking ourselves here is, what is the angle whose sine is 1/2? I think it's very helpful to have a kind of an idea of where we are in the circle, on the unit circle, if you want to call it that. So for sine, I'm going to remind us, first of all, that -π/2 is down here, +π/2 is up here, and I'm going to color in the region. I don't think I want to use blue. It's a little bit too hard to see. This green's not much better, but we'll stick with that for now. This is the region from which I can take angles to answer all of these questions. Okay, so I'll grab my pen here. This is -π/2 to π/2. I have to be somewhere in this range of values, somewhere in this window, if you will. I'll go ahead and label these -π/2, +π/2, and 0. If I draw a generic angle in here, this is the angle I'm looking at here, and remember from our work with right triangle trigonometry, we defined the sine as the opposite, and then in the next chapter we called that y, over the hypotenuse, which we called r, right? So you could think of this as opposite, and this is hypotenuse. But there's also an angle, potential angle down here. Let's do this, and that would be y, or opposite, and this here would be r, or hypotenuse. This is my hypotenuse here. And I can take an angle from either of these two quadrants to answer this question. The problem is that the 1/2 that I was given is positive. So I have to have a positive opposite over hypotenuse. And down here in quadrant 4, between -π/2 and 0, the opposite is going to be negative, right? That y value is negative, and hypotenuse radii are always positive. So I can't use an angle from quadrant 4. I can't use the angle between -π/2 and 0. I have to use the one between 0 and 2π. And the one from quadrant 1 is usually the one that kind of comes to mind anyway. So whose sine, which angle has a sine that's 1/2? The answer is π/6. So that's the answer to that question. All right, let's take a look at the next one. The sine whose angle is -√3/2. Well, the sine whose angle is √3/2 is π/3. But the angle whose sine is negative root 3 over 2 has to be in quadrant 4. It has to be between negative pi over 2 and 0. So now I am in quadrant 4. So this is my reference angle, but I'm down here in quadrant 4, so it's going to be negative pi over 3. Remember that sine is positive in quadrants 1 and 2 and negative in quadrants 3 and 4. All students take calculus. All, that's everything, is positive in quadrant 1. Only sine and its cousin cosecant are positive in quadrant 2. Tangent and cotangent are positive in quadrant 3, and secant and cosine in quadrant 4. I'm dealing with sine and its inverse, so for it to be positive, it has to be in one of these two quadrants. If I'm in either of the other two quadrants, then it's going to be negative. Because I'm dealing with sine inverse, we cannot play with sine inverse in quadrants 2 and 3. We can only play with it in quadrants 1 and 4. There is actually another angle out there whose sine is negative root 3 over 2, and that's in quadrant 2. But because I'm using sine inverse, I can't use that quadrant. I have to use the angle that I can use to solve this problem has to come from quadrant 4. Okay, here's our last one. The arcsine of root 2 over 2 just means what is the angle whose sine is root 2 over 2? And the sine, the value that is, when you evaluate this angle, you take the sine of this angle here, you get positive root 2 over 2. Because this is a positive value, I have to be in quadrant 1. And the answer there is pi over 4. Because the sine of pi over 4 is root 2 over 2, the arcsine of root 2 over 2 is pi over 4. Okay, I thought of another one I'm going to throw at you just because it's a really good, it's a trick. You have to be on your toes with one like this. Now, the square root of 5 over 2 is not one of the answers to our nice angles. The sine of pi over 4 is root 2 over 2. The sine of pi over, think about this for a second, the sine of pi over 3 is root 3 over 2. There is no answer that's the square root of 5 over 2, so that we'd have to do on a calculator. But more importantly, what is the square root of 5 over 2? Well, 5, I think you would agree with me, is between 4 and 9. And if I take the square root of all of these, I get 2 is less than root 5 is less than 3. So, where's my pointer? Root 5 is somewhere between 2 and 3. It's bigger than 2 and smaller than 3. But because it's 4 is so close to 5 and 9 is much farther away from 5, I could argue that the square root of 5 is much closer to 2 than it is to 3. So I'm going to call it 2 point something. And I don't want to get too carried away with details, but let's just say that this is approximately, I'll go ahead and use that sign correctly. So the arcsine of the square root of 5 over 2 is approximately the arcsine of, let's just call it 2.2 over 2. And that's approximately the arcsine of 1.1, just reducing my fraction here. Now, the problem here is that what we're asking, remember, when we ask for the arcsine or the sine inverse is, what is the angle whose sine is 1.1? Think about that for a second. Which angle in the unit circle, or which angle on the, it might be easier to think of it this way. There's 0, oops. There's 0, there's 2 pi, and a sine graph looks something like this. Oh, that's actually not too bad. Which angle along the x-axis here produces a sine or a y value of 1.1? If it was 0.9, I could say, well, maybe it's that one there, or maybe it's that one there. But sine doesn't get bigger than 1, right? Sine never gets bigger than 1. So this is too big an input. And the answer is undefined, or depending on the context, depending on where you're answering this question, you might say DNE, which stands for does not exist. Okay, this is an undefined value. We cannot find the inverse sine of 1.1. We cannot find the arcsine of anything bigger than 1. or smaller than -1, because it doesn't exist. Sine does not spit out a value bigger than 1, ever. Okay, there are just a couple more things I want to talk about in this video. One of them's pretty quick, so we'll do that at the end. But the other one's closely related to this and what we were talking about on the previous screen. So we'll talk about that one next. At the end of the slide, a couple of slides ago, I mentioned this. If you take the sine inverse of something, this value here is going to be a number. When you take the sine inverse of that number, that's going to be an angle. The angle can be anything, right? The angle can be anything, but to take the sine inverse of it, we have to restrict sine from -π/2 to π/2. So if you're dealing with the sine inverse of a sine, you have to restrict the domain on sine. If you're taking the sine of a sine inverse, well, this number here is going to be between -π/2 and π/2 because it's a sine inverse. But when I take the sine of that value, it could fall anywhere between -1 and 1. So this is what I was talking about in the end of a couple of slides ago. Let's do an example. All right, so I'm going to ask you to evaluate the sine of the sine inverse of a number and the sine inverse of the sine of a number. Looking at both of these examples, what goes in this box right here is an angle because I'm taking the sine of an angle. So let's pick an angle. Let's do 5π/4. What goes into this box is the answer to a question. If I give you an angle, give me a number, right? So I'm going to give you like the square root of 2/2 or -1/2 or 0 or something like that. That's going to go in there. And then the answer to this inside piece here is going to be an angle. Once I know what that angle is, I can take the sine of that angle. So there's a restriction built in here, but when I take the sine of that angle, it could be anywhere between -1 and 1. So I'm going to use the value -1/2 in here. So inside the parentheses here, I'm asking myself, what is the angle that has a sine of -1/2? I'm going to draw myself a little four quadrants. Because I'm dealing with sine and sine inverse, inside the parentheses here, I have to be cognizant of the fact that I'm only allowed to play in this playground, right? I'm only allowed to work with values between -π/2 and π/2. I can't talk about sine inverse anywhere else. Now, if you take the sine of an angle, the answer is going to be positive in quadrant 1, and negative in quadrant 4, because only cosine and its cousin secant are positive in quadrant 4. Sine is negative there. And so I want my sine to be negative. So I want, this is the sine, -1/2 is the sine of some angle. That's what this inverse means. -1/2 is the sine of some angle. Since it's negative, that angle must be in quadrant 4. So what angle has a reference angle in quadrant 4 so that opposite over hypotenuse is a half? This is actually -1 here, right? And that angle, if we think about just the reference angle, the sine of an angle is a half when the angle is π/6. So I can rewrite this as the sine of the angle whose sine is -1/2. And that's π/6, that's my reference angle, but because I'm in quadrant 4, my angle has to have been negative. Okay, what I've done is evaluate this inside piece. For this, I get -π/6. Now I have to take the sine of -π/6. Well, the sine of π/6 is a half, but because I'm in quadrant 4, this piece we've done before. This problem we know how to do. It's this piece that we didn't know before. This part here we've already done. The sine of -π/6 is -1/2, because opposite over hypotenuse in quadrant 4 is negative. Okay, now let's take a look at what happens when we reverse the roles of the sine and the sine inverse. This can get messier, by the way. Perhaps I should do another example. Let's go ahead and do this one first, and then I'll come back and do another one of these. All right, now in this case, inside here, I'm going to evaluate the sine of 5π/4 and then take the inverse of that answer. Notice, by the way, I'll back up just for just a second here, that when I did this problem here, this was like saying the sine of the sine inverse of x equals x. I'm getting x out. But that's partly because this value of x is between -1 and 1, right? On the number line, -1/2 is right there. It's between -1 and 1. If my answer had been out here somewhere, well, that would have been a different story. That's partly why I feel like I should probably do another example, but we'll do the other one first, and then we'll come back to that. All right, the sine inverse of the sine of 5 pi over 4 is equivalent to the sine inverse of whatever this is in here. Well, what's the sine of 5 pi over 4? Let's see if we can find a couple different ways we could do that. That'd be 4 pi over 4. One more pi over 4 gives me 5 pi over 4. So my reference angle is pi over 4. So this angle here, let me do that in a different color. This angle here, the pink angle, is pi over 4. So this is equivalent to taking the sine of pi over 4, but because we are in quadrant 3, which produces a negative sine value, I'm going to change this up a little bit. I'm just going to write it a little differently. The sine of pi over 4, that's the numerical part, but my answer will be negative. All right, what is the negative sine of pi over 4? Well, let's start with the pi over 4 part. The sine of pi over 4 is root 2 over 2. And the negative sine of pi over 4 is negative root 2 over 2. Okay, that's the inside part. That's the part we already knew how to do. Now we're going to take the inverse sine of that. What's the sine? What's the angle whose sine is negative root 2 over 2? Well, because we're now dealing with sine on the outside here, I have to restrict my search for that angle to quadrants 4 and 1. I have to stick to these two quadrants. Because the input value here is negative, my angle must have been in quadrant 4. So I'm looking for an angle whose sine is negative the square root of 2 over 2, and that angle is pi over 4. So I get the sine inverse of negative root 2 over 2 is negative pi over 4. Notice that in this case, the sine inverse of the sine of x did not result in x. It did not produce the same answer as the input was. And that's something we have to be very careful for. That's careful with. That's why we have to go through this process. Otherwise, we'd just be able to say, well, sine inverse of the sine of x is always x. It's always this number here, right? That was true in this case, but it's not true in this case. So we have to be careful. We have to go through this process of checking what our domain is for the sine inverse, checking what quadrant the angle, this angle is in. In the case over here, we have to make sure that we're working in the right two quadrants for sine inverse first, and then taking the sine. You have to walk through that process. Okay, I am going to do another example on this side. I'm not sure whether I need to do it here yet. I'll come back to that. But I am going to do another one on this side because there are times, is it this side that I want? Yes, there are times when I don't have the answer to the sine of a nice angle. This is one of the angles that we were familiar with from our very first explorations of radians. We have pi over 6, pi over 4, and pi over 3. And then to that we added pi over 2 and 0, or 0 and pi over 2. And then we started looking at the negatives of those. So those 5 angles in with their reference angles in the 4 quadrants, those are our sort of friendly angles. We don't always get, the answer isn't always going to be a nice angle. So the answer, the input here is not always going to be something from that chart. All right, so I'd like to do an example now where this number here is not a friendly answer, but we can still work out the answer to the question without necessarily having to resort to a calculator. So what I'm going to do here is erase the input and then erase well, actually, I think I'm going to erase this as well and just give you a different kind of input. Let's go with 5 over 13. Now, the answers to the sine of an angle that I'm comfortable with are the sine of pi over 6 is a half. The sine of pi over 4 is root 2 over 2. The sine of pi over 3 is root 3 over 2. The sine of pi is 1. The sine of 0 is 0. Those are the only ones I know as exact values. But the sine is opposite over hypotenuse. Notice, first of all, that this is a positive number. So the answer to this is going to be in quadrant 1. So my angle is going to be something like that. And I know, because I know that it's sine, the sine of some angle, that's the answer I'm pointing to. The sine of some angle is 5 over 13, but the sine of any angle is opposite over hypotenuse. So the sine of this angle is opposite over hypotenuse, 5 over 13. Well, now I have two sides of a right triangle. So I can find the third side. In this case, I don't need to. I just need to figure out what the sine of this angle is. Well, the sine of this angle is 5 over 13. So in this case, I have the sine of the sine inverse of x equals x. I think it's important to point out that there is another angle out there whose sine is 5 over 13, right? All students. So sine is positive in quadrant 2. Sine is positive here. Sine is also positive here. And then we have tangent and cosine. So this angle here, actually, it's this angle here. I always do that, but this is the reference angle. The white angle here is the reference angle. The sine of this angle is also 5 over 13. The problem is I can't take its inverse. I can't take the sine inverse of 5 over 13 in this quadrant because it's not in quadrants 4 or 1. I can only take this sine inverse if it's in quadrant 1. So the angle that is the answer to this question has to be in quadrant 1. Okay, there's one last thing we need to do here, and that is to talk about how to use your calculator to evaluate sine inverse values. Remember that the sine inverse is the angle whose sine is, in this case, 0.1. So how do you do that? Well, you'll notice on your calculator, you've probably already noticed that there are 3 buttons, sine, cosine, and tangent. And in fact, we've talked about these in a previous video. We talked about the fact that if you wanted the cosecant of an angle, you had to take the sine of that angle and then divide 1 by that number, because that's equivalent to cosecant of theta. So we've talked a little bit about those 3 buttons already. Over those 3 buttons, at least on my calculator, I can see sine inverse, cosine inverse, and tangent inverse. So if I want to take the sine inverse of 0.1, I have to hit the second button. It's sort of this kind of shape. And then the sine button, because I've hit second first, it's going to put sine inverse on the screen. So my screen now looks like this, sine inverse and an open parenthesis. I'm going to type in 0.1 or just 0.1, close the parentheses, and hit the enter key. Okay, and that gives me, let's see what does that give me. I had a different value in here a minute ago, so 0.1, and I get I'll put it over here, 0.100167. Okay, so I'll round it. And that's the answer to what is the sine inverse of 0.01. I can use my calculator for any of these other ones as well, but with this one, it's not a nice angle. I don't have the option to just draw a triangle or take the value from a chart because it's not on the chart. So there are times when you'll need to be able to do this on a calculator. Okay, that's been a bit of a slog, but like most of the things we've talked about so far in this course, the first application of a new idea is usually the one that takes the longest to go through. We're now going to talk about cosine inverse, tangent and cotangent inverse, and secant and cosecant inverse. We'll do them one at a time, but this shouldn't take as long because now you have the idea. All we need to do is apply those same logical concepts to those other trigonometric functions. So that's it for this video, and I'll see you in the next one.